In this video, we continue our discussion on electron configurations and chemical periodicity in Chapter 8. In this one, we're going to look at our quantum mechanical model and the periodic table. So based on our last video, as we see at the bottom here, we have this concept of electron configuration. It's a shorthand notation to designate the electron quantum states, assuming off-bound ground state behaviors. So here, for the first 10 elements in this figure, we see what we call the electron configurations. So we'll start off in the upper left-hand corner with hydrogen. Hydrogen has an atomic number of 1 and 1 electrons, so it would have an electron configuration of 1s1. That is, there's 1 electron, and that is in the principal quantum number 1 state in the s angular momentum equals 0 state. Helium has 2 electrons, and there are 2 spaces for electrons, so we designate that as a 1s2. Moving to our next element, we have lithium. Lithium is atomic number 3 electrons, so this would be 1s2. There's no longer any location to put electrons in there. We know we have to have 4 unique quantum numbers from the Pauli principle, so the next lowest energy state we can go into would be the 2s state. So we have 2s1. Next to this, we have beryllium, and this is a 1s2 and 2s2. Now, once we've reached beryllium, we've filled up all of the s's in the principal quantum number 1 and 2 state. So we're going to need to move on to the p orbitals. We know that there are 3 p orbitals because the m sub l values can be plus 1, 0, and minus 1, and the ms can be plus or minus a half. So in those 3 orbitals, we'll be able to fit 6 electrons. And that's what we see when we start with boron. So atomic number 5, boron, has an electron configuration 1s2, 2s2, 2p1. When we get to carbon, it's 1s2, 2s2, 2p2. When we get to nitrogen, we have 1s2, 2s2, 2p3. That's the location for all 7 of the electrons. For oxygen, it's 1s2, 2s2, 2p4. When we get to fluorine, 1s2, 2s2, 2p5. And then neon completes this series with 1s2, 2s2, 2p6. So we remember that the p sublevels, there are 3 different orbitals. Each of those 3 orbitals can take 2 electrons, and so we can have up to a p6. You can't have p7. So S has a maximum of 2, P will have a maximum of 6, D will have a maximum of 10, because there are 5 states for -2, -1, 0, 1, and 2. And then F will have 14 spaces for electrons, for -3, -2, -1, 0, +1, +2, and +3, each holding 2 electrons. So these give us the electron configurations. So these electron configurations turn out to be very important. They're things that you should know how to work with and handle. They require you to work through them, do some practice problems, but they're really not terribly conceptually difficult. I think you won't have too much trouble with them. But if you do, of course, we have time and discussion and recitation. So now let's look at what we'll call partial orbital diagrams and condensed configurations. And let's take aluminum as our example. Aluminum has an atomic number of 13. So there are 13 electrons. So then if we were to write down the electron configuration and following that energy level diagram we saw in our last video, we would fill it as 1s2. Then the next 2 would go into the 2s2. Then the next block goes into the 2p6. So that gives us a total of 10 electrons. And those 10 electrons, as we'll see, let's just take one slide back. 10 electrons would be the same as neon. If we look at neon over in the lower right-hand corner, that's a 1s2, 2s2, 2p6. So now we have 1s2, 2s2, 2p6. That's 10 electrons. Then we have the 3s2 and then 3p1. That gives us a total of 13 electrons. What we're going to find is that the electrons that are the last in are the first ones to participate in chemical reactions. So, for example, when we have this particular element, aluminum tends to form a +3 charge state. That really involves those 3s2 and 3p1 electrons. So what we'll sometimes do, you notice the red underline, sometimes we'll simply write down what we'll call a valence electron configuration, which is a 3s2, 3p1. Or we'll write an orbital diagram, and we won't write down all of the electrons. We'll only write the ones that really matter for chemistry. And those are the 3s and the 3p, so we'll draw them out like they're designated here. 2 electrons in the 3s, and then 1 in the 3p sublevel. So we're looking at only the highest energy sublevel being filled. The condensed electron configuration has the element symbol of the previous noble gas in square brackets. So the 1s2, 2s2, 2p6, which would be equivalent to what neon has, we simply write this down in the following format. Neon in brackets, and that implies that it has the neon electron configuration, followed by 3s2, 3p1. 3s2 and 3p1 then are the electrons that get involved in the chemistry. And the neon, as we'll see later on, we'll term those core electrons. And they really don't participate in any chemical reactions. So now, just to reiterate, orbitals can be designated with boxes, circles, or lines. These are all equivalent. And one other note, in future chemistry courses, you're going to often see single-headed arrows to designate one electron. But Silverberg will use double-headed arrows for his electrons. Now here would be orbital diagrams and electron configurations for the next elements in the row below the ones we just looked at. So atomic numbers 11 through atomic number 18. So these 8 elements, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, have the following orbital diagrams. And notice they all are filling the same principal quantum number, that is 3. So the 3s and the 3p sublevels are being filled. And so for sodium, we put 1 in the 3s. Magnesium puts 2 in the 3s. Aluminum puts 2 in the 3s and 1 in the 3p. Silicon, 2 in the 3s and 2 in the 3p. And notice the 2 electrons in the 3p have parallel spins in opposing or in separate orbitals. So the electrons have a little repulsion relative to one another, and so they tend to separate into different orbitals. Phosphorus has 3 electrons in the 3p sublevel, and they all separate. And when we get to sulfur, the 3s2, 3p4, 2 of the electrons must pair up in the 3p. Chlorine, 4 of the electrons pair up in the 3p. And then for argon, all the electrons in 3s and 3p are all paired. Our electron configurations are written out, and you can see all of these down there. You can take sodium as an example, 1s2, 2s2, 2p6. And then we're simply adding electrons to the 3 level. 3s1, 3s2, 3s2, 3p1, 3s2, 3p2, and so forth, all the way down the column. And we notice that every one of them has the same core group, that is the 1s2, 2s2, 2p6. So for our condensed electron configuration, we simply write neon 3s1. And for magnesium, we write neon 3s2. There's also our valence electron configuration, which wouldn't even include the neon. They just write 3s1, or for magnesium 3s2, or for aluminum 3s2, 3p1, and so forth. Now let's look at periodicity and our electron configurations. So electron configuration and group. And remember, a group is a column in the periodic table. That column represents a list of elements that all have similar chemical properties. Now, based on our model, elements in the same group of the periodic table have the same outer electron configuration type. And we know that elements in the same group of the periodic table exhibit similar chemical behaviors. That's why they're there. So we see that similar outer electron configurations correlate with similar chemical behavior. This is our rationalization. So, for example, everybody in group 1 has an S1 configuration for their outer electrons. Whether it's hydrogen with 1s1, lithium with a 2s1, sodium with a 3s1, and then you'll see potassium as a 4s1. They're all S1s, and the S1s all tend to ionize and react very similarly to one another. In group 2, beryllium and magnesium are both S2s. We've got 2s2 or 3s2 for beryllium and magnesium, respectively, and they behave chemically similar. Boron and aluminum, they have similar oxides. They're both energetic materials. Boron and aluminum have both been used in rocket fuels because they have similar properties. They're used as opposed to other elements because they're very chemically similar, and they both have good properties for rocket fuels. So we have outer configuration that's an S2P1, so it's 2s2 2p1 for boron, and 3s2 3p1 for aluminum. And even though the principal quantum numbers are different, and we do get a little bit of differences there, the overall properties between boron and aluminum are more similar than they are between boron and any other element, or aluminum and any other element. Next, we have carbon, which is a 2s2 2p2, and silicon, which is a 3s2 3p2. These are very similar elements. Nitrogen and phosphorus, likewise. Oxygen, sulfur, and so forth. So you can see the entire first 3 rows of the periodic table show this sort of behavior where our model has them having a similar outer electron configuration type. Now this is a bigger table showing 18 elements all the way across the 4th row of the periodic table, starting with potassium and going all the way across to krypton. And you can see in this case, we're filling the 4s and then the 3d and then the 4p. The reasoning we're filling this is when you broke down the degeneracy of the principal quantum number 3 state, the 3d moved up higher in energy than the 4s. The 4s has got better penetration, and so it drops down lower in energy. Now this is on the filling cycle. We'll see some differences a little bit later in this chapter. So here we see we see our atomic number, element, partial orbital diagram, full electron configuration, and then the condensed electron configuration. What's worth noting here, let's go through this. Potassium has a 4s1. Calcium comes up next with a 4s2. Now, once the S's are filled, and then starting with scandium, we need to go to the D's. So we have a 4s2 3d1, titanium is 4s2 3d2, vanadium is 4s2 3d3. Now comes an exception. Atomic number 24, chromium. You might predict from the pattern it's going to be 4s2 3d4. But it shows different behavior. And the behavior is consistent with this type of electron configuration. It's a 4s1 3d5. So the magnetic properties of chromium tell us that there are 6 unpaired electrons, and that's consistent with a 4s1 3d5 valence electron configuration. Why does this happen? Well, the rationalization is that a half-filled 3D subshell is a favorable energy state. That's more favorable than the 4s2 3d4. So a half-filled 3D subshell, that is where every orbital has 1 electron in it, is a more stable configuration. Then we continue with manganese, 4s2 3d5, iron 4s2 3d6, cobalt 4s2 3d7, nickel 4s2 3d8, and then our second exception in this row is copper. We might expect a 4s2 3d9, but we see it's a 4s1 3d10. And the rationalization for this is that a fully filled D subshell creates a more stable configuration. And to the extent that one can do that, we see that happens. Now, while it doesn't happen in nickel, it does happen with copper, and the spin of copper is consistent with a single unpaired electron, and spectral behaviors is consistent with that electron being in a 4s state. And then from zinc, we continue on 4s2 3d10, and once we get to gallium, then we begin filling the P subshell, 4p1s, the 4p2 for germanium, and then all the way down to krypton with up to 4p6. And now the P subshell has been filled. So let's note the unique behavior of chromium and of copper. Chromium has a 4s1 3d5. A half-filled B sublevel is more stable than having the 4s2 3d4. And then we have copper at 4s1 3d10. A filled D sublevel is more stable. And this does extend to some common oxidation states of these in nearby atoms, as we'll see. But we'll also see some more complicated behavior in a moment. But you should understand all of the electron configurations through the first 4 rows of the periodic table. So here is a full periodic table, and this periodic table then has the partial or the valence ground state electron configurations for all the elements in the periodic table. So you should take some time and look these over. Look at the trends. You'll notice, for example, in brown over on the left-hand side of the main group elements, and in group 1, everybody is an S1. So whether it's hydrogen, lithium, sodium, potassium, rubidium, cesium, or francium, it's an S1 configuration. In group 2, they're all S2s. Where things get complicated is in the transition elements, that is the D block. And we're not going to have you learn things beyond the first row. We have some nice explanations for the few exceptions there, and the rest follow nice patterns. But things can get quite complicated. Let's look at group 10. Group 10 is in the transition block. You can see it's about 2/3 of the way over to the right-hand side, and it starts with nickel. We have nickel at the top of group 10. That's a 4s2 3d8, as we just said in our last table. Right below nickel is palladium, but that's not a 5s2 4d8. That's a 4d10. And then below palladium is platinum. And platinum isn't like palladium or nickel. Now, their chemistries are all quite similar, but their atomic spectra are consistent with the electron configurations as listed. So the spins of the atoms, the magnetism of each of these atoms, and their atomic spectra are consistent with the electron configurations that are shown. And there are complicated rationalizations for each one of these. You can see that right next to nickel, on the left-hand side, we have cobalt, rhodium, and iridium. Rhodium is different than cobalt and iridium. You can see next to that in group 8, osmium at the bottom is different. So there are a number of exceptions throughout this region of the periodic table. The transition elements in the D block show the most exceptions. And so you won't need to concern yourselves with knowing all the electron configurations for the elements in the middle of the transition elements. Now for the main group elements, that is the P block on the right-hand side, so that's kind of the lighter brown color. These all show patterns that are very regular. There's no exceptions among these groups, so they're very nicely behaved. You can see in group 13, that's the one on the left-hand side, leftmost part of the light brown block is boron, B, and that's a 2s2, 2p1, and you'll see all the elements down follow an s2, p1 configuration, starting with boron, going down to aluminum, going down to gallium, going down to indium, and going down to thallium. And you'll see every column in the main group P block follows the same electron configuration pattern as the first row of elements in that block. So these are well-behaved systems. At the bottom, of course, the gray block, the intertransition series, there are some more complicated behaviors here, particularly in the middle of that, element number 64, that's GD, that's gadolinium. You can see it has a 4F7, and that's to create a half-filled subshell. And then you can see 2 over, we have dysprosium, and that ends up having a filled 4F. But the patterns are more complicated here. So you're not going to need to worry about the gray elements or the lower 2 rows of the transition elements. You should know the period 4. So basically periods 1, 2, 3, and 4. And you should recognize the main group elements in the S block and the P block and understand those patterns. They're well behaved. So here's our orbital filling pattern and how this fits in with the periodic table. This is a nice illustration showing how we go from 1s to 2s to 2p to 3s to 3p, then 4s, 3d, 4p, 5s, 4d, 5p, and so forth. This shows the effect of penetration, and that is that shielding effect where the 3d is no longer grouped with the 3s and 3p. Its energy rises up to a higher level. And you can see for all the S block, we're filling the dark brown elements. For the F block, we're filling the gray elements. For the D block, we're filling the blue elements. For the beige or light brown block, we're filling the P block elements. Now, this is a common aid to memorize the subfilling level. You're not going to need to memorize the subfilling level since this is an online course. You'll have access to your text. And so in-class courses up till this last semester, we always required students to memorize the filling level so that they could handle things all the way up to, for example, element lead. And you can see lead up here is element number 82, and so you got to put 82 electrons in, and they follow a nice pattern. You can look at this, but you're not going to need to memorize it. The N value is constant horizontally, the L value is constant vertically, and the N and L, N plus L is a constant diagonally, and so that allows you to have this as a memorization tool. So N plus L being a constant kind of leads you to your correct orbital filling pattern. But you will need to recognize some electron configurations and a few exceptions, and also for ions as well. Next, let's look at what we're going to call categories of electrons. Now, there are some much deeper complications here. We're not going to worry about the complications. We're going to work on the basic principles. And these basic principles will allow you to understand a lot of really important experiments, X-ray behavior, chemical behavior, and so forth. So we have electrons in energy states, and then we'll identify those electrons in their energy states in groups. And there's 3 groups that we'll look at. And the groups are not exclusive to one another. They can overlap in some ways. So the inner electrons are also called the core electrons. I've used that phrase up to now. These core electrons are simply those electrons an atom has in common with the previous noble gas in the periodic table, as well as any completed transition series. So when we get to the mechanics videos for this chapter, we'll go through some example problems where we'll count out inner or core electrons for various types of elements. The outer electrons are those with the highest energy level. That is the highest principal quantum number or the highest n value. That's fairly straightforward. And finally, the valence electrons. Those are electrons that are involved in chemical interactions or forming chemical bonds. And there's 2 groupings to think about. For the main group elements, that would be this S block, that's the dark brown block, or the P block, that was the light brown block in our previous periodic table. The valence electrons are the outer electrons. That is, they're the S plus the P electrons. For transition elements, the valence electrons also include the outer electrons and any of the D electrons in the unfilled D subshell. We'll look at examples of this later on. Now, next we're going to define atomic size, and there are 3 things to look at to defining atomic size. And your book talks about all 3, and I put one on here because the book has a pretty significant error that can be misleading. So we're going to identify that error. First off, we have what we call the size of the atom. Now, if you have an isolated atom floating around in free space, and let's say it's in outer space, let's say you have an argon atom floating in outer space, defining its size becomes a little bit difficult. The reason it is because the electron turns out to be delocalized. So when you go to measure it, you'll see that their electron, of course, since the electron has wave properties, it actually delocalizes over space. It does not have a defined position. So it's not like you can stick a ruler on it and check the 2 outside edges of the electrons because they're waves. But once we put elements into their elemental form, into like either a solid state form for the metal or for the nonmetals that are solids, or if we have nonmetals that are diatomics, we define the atomic radius of a system as simply half the distance between the nuclei. Let's take as an example the upper left-hand corner. The upper left-hand corner has aluminum here. Aluminum in the brown balls, aluminum forms, it's a crystal structure called face-centered cubic, which is discussed in chapter 12. But it forms a structure where the aluminum atoms are next to each other. So in an aluminum solid, aluminum atoms are next to one another and they chemically bond with one another. And the distance between 2 adjacent or 2 closest nuclear centers inside the crystal is 286 picometers. That's the aluminum nucleus to aluminum nucleus distance. That can be defined fairly precisely using X-ray diffraction techniques. And so half that distance is 143 picometers, and we would call that the metallic radius of aluminum. And that's a measurable value. So that's what we're going to use as what we'll call the atomic radius for aluminum. Now, if we have chlorine, Chlorine doesn't exist as it's a gas at room temperature, it's not a solid, and it's a diatomic gas. So identifying its radius is a little bit different. We can measure the distance between the two chlorine atoms in the chlorine molecule. That distance is 199 picometers. And so we'll call that half that distance the covalent radius of chlorine. And so that is a measure of the atomic radius of chlorine, though it's, as you can see from the picture, it's not exactly what we would visualize as the radius for a single atom of chlorine. So that's what we'll call the covalent radius. Now your book also has something in it, and it indicates that it says, known covalent radii and distances between nuclei can be used to find unknown ones, or you can add together two covalent radii for two different atoms, and that'll tell you what the bond length is. And that is simply incorrect. And it is incorrect most of the time. That's why you should mark this out in your book as incorrect, and we will not use that. We will not do problems on that since it is incorrect. So now that we have some measure of atomic size or atomic radius, we're going to look at the trends in atomic size or atomic radius. So as we go, for example, from boron, which is 2s2, 2p1, to aluminum, which is 3s2, 3p1, what is the trend in size? You know, you might suspect aluminum is bigger. In fact, it is. And let's see what the trend looks like. So atomic size tends to increase as the principal quantum number, n, increases. We know that as n goes up, you're getting further away from the nucleus. And so as n increases, the probability of the outer electrons to be farther from the nucleus increases. So the atom is bigger. It takes up more space. It occupies more space in solids, and its bond length in compounds are larger. So atomic size, the size of an atom, as we can measure size, increases as the principal quantum number n increases. So as we go from row 3 to row 4 to row 5, as we go down the periodic table, the atoms get bigger. But next, atomic size decreases as the effective nuclear charge increases. So now when n goes up, z goes up, but within a given row, within a fixed row, as you go from left to right, the effective nuclear charge increases, and so the size goes down because we have a fixed principal quantum number. Therefore, for main group elements, atom size increases down a group and decreases going from left to right across a period. Let's look at this. So in this figure here on the right-hand side, you can see a series of boxes for the elements, and inside each box is a circle with a number. And that number represents the atomic radius as measured using the methods that we talked about a moment ago, a few slides earlier. So you can see hydrogen, of course, is quite small. 37 picometers is that radius. Lithium is 152 picometers. Sodium is 186 picometers. Potassium 227. Rubidium 248. Cesium 265. So as we go down group 1 from top to bottom, the atoms get bigger and bigger. If we go to group 2, beryllium, magnesium, calcium, strontium, barium, and radium, the atoms get bigger going down. Group 3, group 4, group 5. We see all these trends, and they behave quite well. Now let's take row 2 of the periodic table. So now we'll start at lithium and go from lithium to the right. So we see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. You'll notice that lithium has the smallest atomic number, but the biggest size. And as you go from lithium across, you can see that the atoms get smaller and smaller. So the reason the atom is atomic radius decreases going from left to right is because you have a fixed inner core. That is, everybody in the second row from lithium all the way over to neon has the same core electrons, and that is helium. But the nuclear charge is increasing. So from lithium, it's 3, and by the time we get to neon, it's 10. And so in that case, we have increased our effective nuclear charge from 1, which is lithium, because we got 3 nuclear charges, but 2 electrons that shield it, so the effective nuclear charge is 1, all the way over to neon, which has a nuclear charge of 10, but 2 inner electrons, so its effective nuclear charge is 8. And so as the effective nuclear charge goes up, the electrons that are on the outside get pulled in more and more tightly. And as they get pulled in more and more tightly, the atomic size gets smaller. And then as we go from top to bottom, as in B, as we go from top to bottom, we're increasing N. We have more inner shells, better shielding and lower electron attraction, but we're also going to higher principal quantum number, and that tells us we're going to a further distance from the nucleus. So this is the trend in atomic radii for the main group and the transition elements. Now, when you go across the transition series, you'll actually see that it tends to go down and then rises back up again. It's a little more complex behavior. We're not going to go into that in detail right now. So here's our periodic trend in atomic radius. This figure shows a graph where on the left-hand side you see atomic radius on the y-axis, and then the atomic number on the x-axis. So we're going from hydrogen, atomic number 1, all the way out to radon at our highest atomic number. And we see the atomic radius jumps up when you get to the first element in each row. Lithium, sodium, potassium, rubidium, and cesium. Those all have very large atomic radii. They're what we call soft atoms. And in fact, the metals themselves are soft. You can cut them with a butter knife. They're kind of almost fluffy, if you want to think of it that way. That outer electron is held very loosely, and we know it tends to come off. But if we just look at the metals themselves, we find that they have a very large radii. Correspondingly, the alkali metals have a very low density, because the density is inversely proportional to atomic radius. As atomic radius gets big, the density gets small. As atomic radius gets small, you can pack in more atoms per unit volume, the density goes up. And so there's a very clear trend, and we can see how this is very nicely behaved. Now let's look at a periodic trend in an important elemental property, that is the ionization energy. The ionization energy, often written IE, is the energy required for the complete removal of 1 mole of electrons from 1 mole of gaseous atoms or their corresponding ions. So, for example, element A going to A plus 1 electron, the enthalpy of that process, the standard enthalpy, is the ionization energy of A. Next, taking that ion A plus and going to A with 2 charges, that is A2 plus another electron, that would be the second ionization energy of A. And this can go on until you've removed all of the electrons. And in fact, as we spoke of earlier, our colleague Charlotte Moore has done this for all of the elements and removing all of their electrons. And we always see that the first ionization energy is the lowest, the second ionization energy is the second highest, the third is the third highest, and so forth. Atoms with low ionization energies tend to form cations. We'll see that those are metals. Atoms with high ionization energies tend to form anions, except the noble gases. Ionization energy now, just like atomic radius, has some periodic properties, and it tends to decrease going down a group. Let's think about that first for 1 second. The ionization energy tends to decrease because the electrons are further out from the nucleus. They're easier to remove from the atom. The ionization energy also tends to increase across a period because the atoms are getting smaller, the effective nuclear charge is going up higher, and so it's harder to remove the electrons. And here's a nice picture of this. The group with the highest ionization energy is the noble gases, that is group 18. We see now, this is an inversion of the last graph we looked at. Helium, neon, argon, krypton, xenon, and radon have the smallest atomic radii. They've got the highest ionization energies. And group 1 has the lowest ionization energy because that's the 1s electron is the easiest to remove, or the S1 electron is easiest to remove, and it's the furthest from the nucleus. We can also walk ourselves along a row. Let's just look at this graph just a little bit more closely. Let's start with lithium. You can see lithium on the left-hand side at the bottom of the graph, lithium in brown. So next to lithium is beryllium. You can see that first ionization is higher, and that forms a 2s2 configuration. After that is boron, and boron has a 2s2, 2p1, if you remember that electron configuration. That tells us that the 2p1, now when it's hanging out by itself, is easier to ionize than an S2. And then next to boron, we've got carbon, and then nitrogen, and then boron to carbon to nitrogen would half fill the p subshell. Then the next electron coming in is oxygen, and that's going into a filled orbital. So a half-filled orbital. So oxygen is the first electron that goes into one of the p orbitals that's already got an electron in it, so that's the easiest one to remove. And then we have oxygen, fluorine, and neon filling up the p block. So these trends are pretty interesting. The ionization energies are measurable properties, and in many ways they're very consistent with this electron configuration model that we've developed. So here are the first ionization energies for the main group elements, and you can see, the helium is the highest, cesium is the lowest. Cesium is a very reactive metal, reacts explosively with water because it's so easy to pull that electron off. It reduces the water with the electron to form hydrogen gas, which ignites. So in general, the ionization energy increases across the period and increases down a group. That's an important take-home message on this. Now, the next thing to look at is the multiple ionization energies. And let's take beryllium as an example. Beryllium has 4 electrons in it. Its electron configuration then would be 1s2, 2s2. We can look at beryllium's first ionization energy, and that's shown here. That's the small grayish box. That's 0.9 megajoules per mole. Megajoules is still a big number, but it's 0.9 megajoules per mole. So if we remove 1 electron from beryllium, then we form a 2s1 configuration. The second electron that we remove is the second of the 2s electrons, and that's a higher ionization energy. So second ionization energy of beryllium is going to be 1.76 megajoules per mole. Now, if you want to remove the third electron, you're going to have to get at one of those core electrons, one of the helium-like electrons. You're going to have to pull out one of the 1s electrons, and that requires a lot more energy. The first 2 electrons, the 0.9 and 1.76 megajoule per mole electrons, those have shielding from the inner or core electrons. But when you get to the third electron, it's not shielded much at all. There's one other core electron, but there are no other core electrons that are core to it. And so its ionization energy jumps up almost a factor of 10 from the second ionization energy. Now let's look at the successive ionization energies of the elements all the way from along the second row of the periodic table, from lithium all the way over to neon, and then following that with one element from the third row, that is sodium. So you can see in the unshaded area are the ionization energies for the outer electrons, that is, the ones with the highest principal quantum number. So for example, with lithium, the first ionization energy is 0.52, but the second ionization jumps up more than 10 times to 7.3 megajoules per mole. Huge jump. Now for beryllium, the first ionization energy is a little more than for lithium because of the higher nuclear charge. The second ionization energy is again a bit higher than that. But it's the third ionization energy that jumps up almost a factor of 10. Those are core electrons it's removing. For boron, we see again the first, second, and third ionization energies show a nice steady increase. It's that fourth ionization energy that blows up on us, that goes up almost a factor of 10, because the fourth electron on boron that you're removing is the core electron. This continues with carbon. There are 4 outer electrons, and then when you hit the core electron, we see the big jump. Same thing for nitrogen. We have 5 outer electrons, and then it's the 6th that's the toughest to move. Oxygen, fluorine, and then all the way to neon. Now, once we come back to sodium, that first electron is easier to remove than it would be from lithium. It's the second electron that's hard to remove. So this pattern shows us a couple of things. Ionization always increases going from first to second to third ionization energy and so forth. But we always see a huge jump when you come to ionize or remove the first core electron. That's an important pattern for you to remember.